Hi, everybody. So we worked through an example where we had a charged rod along the x-axis and some point P not touching it, and what was the E field at that point due to the whole charge on the thing. And then we did a ring, which is actually going to show up again in this derivation. And now we've got a plate. And this one would be useful in understanding capacitors, which is something that we're going to deal with quite a lot, and it's kind of like immediately ready to go application. The other two, besides being something you need to know how to do, are kind of stepping stones to this. But besides the process is something that is useful to practice no matter which way you look at it. So there. All right, so when we were last here, on the last episode of Newland Does Physics, I told you that for a ring, and again it was in the x direction, but I'm just going to put subring, the E field due to a ring, which in this case is going to be this dark brown guy here. It's actually going to be a differential piece here, but let's wait. That was, let's see, K times X times the total charge on the ring Q divided by R squared plus, I'm reading, plus X squared to the 3/2 power. Yeah? Oh man, that looks bad. Let's clean it up again. And of course you'll see, I hope you guys will immediately notice that, so R squared plus X squared to the 3/2, that I've replaced A with this variable R this time, and everything else is actually the same. X is how far we are from the center of the plate, which is where the location P is, which is on the x-axis. That axis is again at a right angle, so it's orthogonal to the area of the plate. The plate is in the YZ plane. K is Coulomb's constant, so X is how far away you are, Q is the total charge. And this time R is actually going to be a variable because, and if you've done this sort of thing with calculus before, you could imagine trying to describe the area of a circle using calculus by taking the circumference of one of these rings, like an inner ring of radius dr, and integrating I'll try that again. Integrating over all of the different r's. Well, it's a similar idea here. The charge in this little tiny ring here, which has radius dr, is going to be dq. So one more time. The area that we've got here is going to have a total charge dq on it. So there's our differential charge element this time. It's a little bit different than what we've done before. And that differential charge element dq has radius dr. And from the center of the plate, or the disk, I guess, out to the inside edge is going to be the radius r, and we're going to use all that stuff together. Now, often when we talk about charged surfaces and E fields due to them, we need a constant to describe how the charge is spread out. And since this is an area rather than along a line, like with the rod we talked about before, instead of using lambda as our linear charge constant, I'm going to use sigma instead. So sigma is going to be the charge per unit area as opposed to charge per unit length. So the charge per unit area as opposed to the charge per unit length, which means the differential charge is going to be dependent on a differential area element. And this is where I made that reference to defining the area of a circle using some calculus. Well, here's how that would work. A differential area is going to be the circumference, 2 pi r, of your particular ring. So the radius is r right there. So what's the circumference around it? It's dr. And then multiplied by dr. Okay? So if you were to integrate this expression right here, 2 pi r dr, with respect to r, obviously, you're going to end up with pi r squared. So exactly the kind of thing you would expect. And that's actually where this particular trick came from. So the area inside that brown ring is actually the circumference of the inner ring times the dr. So that's what that would be. All right? So that means now, let's rewrite this slightly. So I got sigma dA equals dq, which is sigma times 2 pi r dr. And I do recognize that it's kind of a leap to take the inner circumference and imagine multiplying it by that dr. But this is not a calculus class, so I'm assuming you have seen that in some other context. At any rate, now I've got a way to relate the differential charge on that little brown guy, little brown ring there, the dq, to the radius. And you'll notice that now I've got a dq over here and an rdr. So you can see how I think ultimately we put all these pieces together, and instead of having a differential charge and a variable r, we're now just going to have a differential r and a variable r. So what would that look like? So E for the entire, so that was E sub ring up there. So E for the entire disk is going to be the, let's see, we're going to have to convert this thing right here into a differential charge. So there's going to be a dq right there. In fact, let's go ahead and write the whole thing out. The integral of k times x over r squared plus x squared to the 3, that's an x, so bad, to the 3/2 power times dq. And the dq is this crazy looking thing right here, times dq. And we don't have any limits on there yet. Wow, I really messed that integral up. Or at least my stuff all piled together there. So we're going to integrate. Now that is an integral. Deep and powerful. I love it. We're going to have to integrate that side. But what we've got here, and this is something we've run into before, we've got a charge element here and a distance there. So let's fix it. Man, that's, I can't believe that's so bad. That's terrible. There, really long, but at least it's clean. So the E field from the entire disk at this point P, which is a distance x away from the disk, is going to be, let's see, what can I factor out? I can factor out, well, I'll tell you what, here's our integral. I'll put it in there first so I can't mess it up. And then I've got, that doesn't mean I can't mess it up, but I'll try my best. So k times x over r squared plus x squared to the 3/2, and then wonk, we're going to have all these constants. Sigma 2 pi, there's an r which is not going to be a constant, and there's our dr, which we've taken the dq right here and replaced it with this crazy thing, all of these constants. And now we've got some choices to make. So everything that's a constant is going to come out in front of our integral. So E for the entire disk at point P is equal to, let's see, what constants we have. We've got k, sigma, pi, and x. And I'm actually going to leave the 2 in there. I'll tell you why in a second. But so k, sigma, pi, and x. Now the 2 is going to stay inside the integral. Oh, why? Why can't I draw integrals, guys? Let's try again. Still bad, but it's better. And I'll come back to the limits here. And so now I've got a 2r dr over r squared plus x squared to the 3/2. Something I didn't mention when I started, in the ring example, I had x squared plus a squared, and everything was a constant, but now r is a variable. So not only have I replaced a with r, which is a variable, I'll put it in the front of this expression. We're going to do some pretty straightforward calculus here, but that's kind of why I rearranged it in the first place. But let's talk about the limits. What would the limits have to be? So let's look at our picture again. So what I'm saying is all of these pieces are constant, but 2r dr over r squared plus x squared to 3/2. Well, what am I integrating from? From 0 radius, which would include no charge at all the way out to r, which should be the entire charge dq, right? So this plate is charged a plus q, just like we did in the other 2 examples, which means, oh, I skipped this before, since we are dealing with just the magnitude of E, which is why I don't have any vector signs on there. Since this guy is positive at point P, the E field is out along the x-axis like we talked about before. And I kind of skipped over that, and I shouldn't have done it. But at any rate, if we're talking about none of the disk at all, so in the center there's no charge. If we're talking about all the way at the radius r, then it's got to be all of the charge. So even though the E field is really dependent on the charge, we use this, somewhat clever, I guess, geometry and calculus to make this an integral in r instead of an integral in x. So let's do this thing. There are a lot of ways to do it, but I kind of what makes the most sense to me is to use u substitution. So I'm going to let u equal r squared plus x squared, which means that du then is 2r, the derivative of x squared, which is a constant with respect to r. Well, x is a constant no matter what, but the derivative with respect to r is 0. So that means du is 2r dr. Okay, so I've got u, I've got du, and I can now actually, make this integral work. Let me flip my notes over here. And such good notes. So I'll tell you what. There. So E disk, again, this is the magnitude of the E field from the entire disk at point P, is equal to that giant slew of constants. Let's see, where was it? K, sigma, pi, and x, k, sigma, pi, and x, all the constants, is now the integral of, instead of 2r dr over r squared plus x squared to the 3 halves, I've now got 2r dr is du. Ah, wow. So unpleasant. Yeah, that's better. Du, and on the bottom where I've got r squared plus x squared to the 3 halves, that makes that u to the 3 halves. Right? And you could, if you wanted, I did this before with my, the example with the rod, I think it was, k sigma pi x integral of u to the negative 3 halves. So now it's a nice, clear, obvious example of a application of the power rule. Yes, I did blank there. Okay, so what you're going to do, forget about it. And I am totally being lazy and leaving off my limits here. I'll come back to what those limits. In fact, they're going to end up being 0 and r when I'm done. So I really should be a little bit more careful. But it's too late for that now. There's no turning back. So the integral of u to the negative 3 halves du, that is, so you add 1 to the exponent, so 2 over 2 plus, or minus negative 3 halves, and multiply by whatever that number is. So I'm sorry, you'll end up dividing by whatever the exponent is. So that means I'll have 1 over negative 1 half. So I'm going to multiply by 2, and u to the negative 1 half. So one more time, I added 1 to this. Whatever that number is, I'm going to say 1 over that here, and that'll be my new exponent. So negative 3 halves plus 2 halves is negative 1 half. So I'm dividing by 1 over 1 half, so I'm multiplying by negative 2. Whew, that was a lot to say. So after that integral, I've got E disk is going to equal k sigma pi x, and then divided by negative 1 half, which is the same as multiplying by negative 2, times u to the negative 1 half. And now would be a good time to, so I don't know, since I was lazy with my limits, let's plug back in for you what I started with, and I can use the limits that I know I need. So E disk is k sigma pi x. I got negative 2 that I almost forgot. And instead of x to the negative 1 half, I've got r squared plus x squared. I mean, instead of u to the negative 1 half, I've got r squared plus x squared to the negative 1 half. Okay, remember this is our variable. This guy's a constant. Still a constant, still a constant, still a constant, still a constant. And so it's negative 2. Hey, there you go. So now, I almost left them out after all of that complaining there. My limits are from 0, no radius, where there'd be no charge, all the way out to r, all of the radius, where we have all of the charge. So this is where my algebra cannot go wrong, or you'll end up with like some terrible skip in the middle of this video where I'm like, and now I fixed it. So let's see if I can avoid that. So E disk, again, the E field at point P from the entire disk is now, let's see, negative 2 times k times sigma times pi times x. Look at all of that giant pile of constants times r squared plus x squared to the negative 1 half from 0 to r, which means I got 1 over r squared. Now it's capital R squared, right? The constant r squared. So the entire disk plus x squared to the 1/2 minus 1 over, and I'll plug in a 0 there, plus x squared to the 1/2, parentheses. Okay, so you'll see that this kind of messy looking thing over here, 0 plus x squared is x squared to the 1/2 is x. So now I've got a 1 over x over here. And we got a negative in there too. We got to make sure to move that negative in there. This negative is going to flip around these two expressions. Okay, so let's do that instead of me trying to skip too many steps. So this whole thing is now 2k sigma pi x, and then I've got, and again, 0 plus x squared to the 1/2 is 1 over x. So now I've got 1 over x minus 1 over r squared plus x squared all to the 1/2 power. So that's what the negative did. I can distribute the x in there, which is, there's not a whole lot more cleaning up you can do, but you can take this x and distribute it to this expression, and you get what is the actual value that we would use, the actual answer. The E field from a charged disk whose charge is plus q and whose radius is capital R at a point P, which is at a distance x away, the E field at that point is, here, let's write it this way, 2 times k times sigma times pi times 1 minus x over r squared plus x squared to the 1/2 power. And I know it seems like this isn't all that useful, but you'll notice that we can, when we get to capacitors, this will actually come back up. And, that's the answer we wanted.